Please welcome Managing Director of Autobrains Germany, Manuel Yoon.
Hi. Yeah, thank you, Oliver. Thank you, Mark. Thanks for having me. It's kind of a wow moment for me because 3 years ago we had the first event and I opened, I think, the conference with a content talk. And it's so fitting also today that we started with Jürgen Döllner, who talked about how AI is eating or ending programming. And now we're ending the agenda with an AI company. So it's a great opportunity for me. And I always remember the quote by Mark Andreessen, who was one of the first VC investors. He put $500,000 into Facebook. And he wrote a big article in 2011 that was called Software is Eating the World. And now people in this time are saying AI is eating software. And I will bring you an example of AI and how we apply AI in autonomous driving and ADAS. And why we need, I think, the next generation of AI to actually solve autonomous driving. So a beautiful AI and software use case from the mobility sector. So I work for Autobrains, and Autobrains, if you don't know it, is an Israeli startup. We're based in Tel Aviv, about 150 people, and I'm leading the office in Germany, in Munich. And what makes us different is that we train our software, so video perception algorithms and so on, not on labeled data, but basically on raw data in a self-supervised and self-annotated way. So when we look at the AI problem of the industry today in automotive and autonomous driving, there are certain extremes of the spectrum. And there is the middle segment of what we call some high-cost ADAS, where you have large domain controllers that we talked about today, where you have actually a decent amount of computing power and data and software. Where you have a lot of sensors that can handle these high cost and high requirement scenarios. And you have also the robotaxis that you can already drive in San Francisco and other cities now that have a lot of sensors, radar, LiDAR, 17 cameras, but they are geo-fenced. So in these inner segments, the actual AI problem is a bit more limited, I would say, or you have helpers to reduce the AI problem. And then you have these two ends, these are the extremes on the very low segment, what we call affordable safety, where you have an AI problem to make, or to use the AI to make a car safe or autonomous with just a single camera. So you have to have very, very low compute and very low memory. Just to enable one single camera that's sitting in the windshield to make a system work at 1 TOPS or 3 watts. And there are very, very few players in this segment. And this is the segment that we focus on with ADAS, where we're actually also going into production end of this year in China. So this discussion for me is very interesting because also for us, the first SOP as a startup in this segment is actually China. And then you have the other end, the extreme, and this for us we see is still not existing, so there's no viable or mature solution yet in AI, this is not solved yet, is how can we make autonomous driving happen, not only in a geo-fenced area, but in a much larger operational design domain with the few sensors that we have available in the car. And there are two approaches that you see today in the industry from an AI perspective. And the first one is to break down the problem into different modules. So the system architecture is a modular architecture, or some people call it compound AI system. So you take the sensor input, radar, LiDAR, cameras, and you break it down into a perception task. So you describe what objects am I seeing, how far is the object, and then you add the localization. Mapping is another module. You try to understand the path of the different objects, you're planning, and then you're sending this to the control. And this is where is an approach that is coming from robotics, and I think in automotive is now a couple of years old. And now we're seeing in the past 6 to 12 months that a lot of the AI players in the field are switching more and more to an end-to-end approach. So this means instead of breaking down the AI problem into these single modules, I say there is an end-to-end network in which I just train on basically sensor input and actuation input. And instead of just recognizing every detailed object, I train this model end-to-end. So this is famous for Tesla here because they introduced this with version 12, FSD v12, and tried to improve the system there. And famously, Elon Musk said they threw out 300,000 lines of code doing this. But we believe that each of these solutions also have their inherent problems and are maybe not the ones that help us get to autonomous driving. And I'll explain why. So why is it difficult or to reach this goal with the compound AI system? There's two problems. So on the one hand side, you may have too much irrelevant information. And on the other side, you're actually lacking information when we are talking about detection. So even with our systems that we train on large data sets in an unsupervised way, you will have a lot of information or detections in the picture that are actually not really relevant from your actual driving tasks, right? So I could say, why do I care about an object that's, if I'm driving 30 kilometers per hour, that is 300 meters away, and why do I have to have a 99% accuracy of detecting this object? And on the other side, there are situations where, from the perception perspective, we would actually like to understand much more, but we have a lack of information. So what is the intention of this child in the image, or the person working there? Will he open the door, yes or not? And we don't have this information from a detection perspective yet. And so the perception and the planning is actually decoupled from each other because it's a modular AI system. And on top of that, even us doing this in an unsupervised way, there's a huge task of data labeling, so annotation services for text for the video data, for the photo data. So there are competitors of ours that have thousands of data labelers sitting in low-cost countries and actually putting bounding boxes on different object classes like pedestrians, cyclists, trucks, vans, etc. And there's a massive data need, so there's petabytes of data floating around that needs to be structured, annotated, etc. And there's a huge cost of labeling this data, and it's also prone to human bias and errors, even if you semi-automate this in a way. So there's quite a few problems with this compound AI approach. And on the other side, also this end-to-end architecture that I showed to you, where a lot of players are gravitating towards now, also has some inherent problems because it is a black box. So when you look at the video of Elon Musk when he introduced this FSD12, it's actually an entire 40-minute ride that he posted on his platform X. You can scroll to minute 20, and the car is actually going over a red light. And the system has never learned what is a stop sign or what is a red light, but it's basically all trained on data and good driving behaviors from good drivers. So now if this intervention happens, you now need to go back into explaining why did this happen in this situation. So you actually have then now a data explanation problem and a traceability problem that you need to go back to your data set and find this, what caused this issue. Because it's not explainable in the sense that because it's an end-to-end network. And the way that now everybody is trying to solve this is solving these edge cases and these last few percents of these edge cases. And from our perspective, we believe that also this approach will at some point hit a wall. Because it's kind of insanity to do the same things over and over again and then to expect different results, right? So because you have such edge cases kind of diluted in your data set, so you're trying to solve this last few percent, but it's kind of exponential what you have to give into the system. and the system is always designed to reduce the average errors. So almost by design, these systems, you can expect them to perform very well on the average, but it may not perform very good in these edge cases. And we're doing similar things in automotive now, like we're doing with large language models, where there's a purpose for this, is to say, let's scale this even more and let's throw more data at the problem. Let's throw more training at this. And we saw the 120 data centers that are being built. It takes more energy, more compute. And just by adding more and more and more, we hope that this error here will reduce, but it's actually an exponential problem that we face here. And so by design, this is very, very difficult to solve. So if these two approaches have their limits, what we at Autobrains like to do is to look at humans. And I had this coffee chat with someone and he said, actually, I'm not such a bad driver. So if we can reach the human level of driving with my eyes, we would actually be already in a very good state. And I have to agree to some point because driving is really a task that is still designed for humans. And these human driving features, today is the human brain is the best reference for good driving. So now, even when you look at this sign here, you already know, like, it takes you a little bit, right? But with your human eyes, you were able to understand and grasp where you want to go. So let's have a look at how systems are designed for humans and try to mimic this. This is what we do at Autobrains, and we believe can be the next generation of AI. And there are two observations for the human from the human brain that are interesting and that we want to use in our AI approach. And then the first one is that we have holistic understanding, and the human brain is very, very adaptive. So it can adapt to different situations and has single intelligences for very specific things. So also you as a human, you don't have one end-to-end network to use ChatGPT, to play guitar, to use Excel, or to drive. So you have single intelligences, like we think about that, that still enable you to see the whole and be very adaptive. And the second observation about the human brain is that we have billions of neurons, but we're not using all these neurons all the time. So they are not spiking and firing on all cylinders in billions of times in your brain. But if you are in a new situation, it's only the necessary, only the relevant neurons that you use. And your brain has figured out which neurons to activate in which situation. And this is actually a sense of your brain has learned how to route the task that you have to the correct neurons. And this is also something that we use in our technological approach. So to sum that up, there is the compound architecture, the first one that we showed you, where a lot of the safe ADAS systems are still built upon, that we will still see. So where we also, for example, provide perception solutions for single cameras, and our tier 1 partners implement then the driving functions. And we see now these lots of players that try to solve this long tail edge problem with a single end-to-end neural network. As said, from our perspective, this is going to hit a wall. And we now want to introduce a new kind of AI approach to solve this long tail of the edge cases. And this is what we call scalable or modular end-to-end networks. So these are skills that can be added for edge cases over time, but they are end-to-end networks, but they are tuned to very specific scenarios or tasks. So think about, you want to have one skill that you have to solve the edge case or the case to drive into a roundabout. Or you have a certain skill on how to overtake a truck. You have a skill on how to drive in the best way through the rain in Berlin, in narrow streets. And then we have a network of these agents that we call skills. And these skills can learn new things over time. So you can add more and more skills over time, the more edge cases you have. And these are narrow end-to-end AI trained agents. And coming to this virtualization also that we saw is perfectly fits into this software-defined vehicle approach, or actually you now have to say it's an AI-defined vehicle approach. So instead of having in the monolithic end-to-end architecture where you learn new situations and now need to retrain the whole network and do an overall software update into the car, you can have multiple skills to be added over time without really retraining the entire thing. So you can gradually add skills. So you can imagine that, for example, your car today with this technology would be able to drive in an unsupervised autonomous way already from Dresden to Berlin. And maybe it also knows how to drive autonomously unter Linden, but it doesn't know yet how to drive autonomously in other areas of the city. But the more it gets exposed to different edge cases in the city, you can add these skills over time. And you have singular updates for these skills. So how this works then from a system architecture perspective is that you get a sensor input and the perception router understands the scene and picks the right skill or the right agent for this scene that has the best capability to solve this task, just like your brain does, and it pulls the information. So you have still the sensor input and the actuation that goes to the car as an output. And by that, you have really a broad network of skills, and you only use the skill that is relevant for the situation. And I will just run the video so how you can imagine this, and we did this with our vehicle in Detroit. We tested this, so you see here situations where the car is driving, and you have this ensemble of narrow AI agents, and the perception router is trying to understand which one has the highest confidence to deal with this situation, and then the perception router picks this skill. And so we've implemented this now in the car and with some of our automotive partners for different driving situations, for example, to come to a stop with a stationary vehicle that's preceding us, or to overtake. And we have these very specific scenarios for which we then train still end-to-end the agents. So we didn't break this problem into a compound AI system, but we said, let's train end-to-end for this scenario to keep the lane, to overtake the cars, to be going in and out of a roundabout. And the system performs quite well, even if you give it the same task, but in a different setting. So then speaking about the I think we had the first conference 3 years ago was called Software Factory, and now there is this term AI Factory, which NVIDIA, Jensen Huang also promoted at one of his conferences, and where we believe a strong trend is going to, that you will find more and more players that are actually building AI factories to help their clients or partners build their own AI. So this is a similar principle here, because we realize that a lot of the OEMs or partners that we work with, they want to have IP ownership over their autonomous driving stack. So we don't develop our autonomous driving stack ourselves, but rather we give the OEM what we call here a skill factory to then take the data from their own fleet using our IP of AI, and then develop their own AI agents or skills and train them, homologate them, validate them, and bring them into the car. So in the shadow mode, you can test it virtually, and then you can have different modes of autonomous driving. Some areas you will still drive supervised, so the driver has to be attentive. And in other areas where I already have the skill to drive autonomously, the system will take over by itself. So it's a much more flexible approach, taking the AI to the road and to implementation. So to sum up, why we believe this approach is the future for us is that you really optimize these end-to-end networks to the edge cases. Yeah? And you also have then explainability because you know which skill was used and why. Since you're not using a big deep learning network, it also has much lower requirements to the compute. So only the agents and skills that are used, you can basically put them into a cache, can be executed in the right time, in real time. And you'll have much shorter learning cycles and incremental learning into the AI systems overall. So I hope I was able to give a nice AI use case from the real world that's also software-based, and hope to have a good discussion with you. Thank you.
Manuel.
Yeah, thank you for the very interesting talk. Two questions. How do you know which kind of model is really suitable for the situation, how to assess the situation? And the second question is, if in the situation something surprisingly occurs, so the model doesn't fit anymore, what happens then?
Mm-hmm. Yeah, so it's similar to the human brain. You learned over time which skill to use. So similar here, we train the perception router, and it gives you a certain confidence intervals for the different skills. So the best skill that you have available is outputted by the perception router, which is also trained.
Hier gibt es eine Frage.
I have a question regarding the edge cases you talk about. So do you have a segregation between driving on the highway or driving in public, for example, in Berlin, in the city? This is the first one. And the second one, you talked about the accuracy, 99.5%. Do you have a target goal which you want to achieve with the error rate? Because it's quite high, so maybe heading Six Sigma that you say this system is able to handle every situation, is driving everywhere and doesn't matter where.
Yeah, so I mean, what we do is we basically break the problem into a finite set of skills, right? So it could be that in the end stage, you have a system of 300,000 or 400,000 of these skills that enable you to drive autonomously in many areas for 99% of the time. But the approach I think is a different approach, is to say, let's democratize autonomous driving and bring it to the streets as early as possible in a safe way for the areas that we are capable of doing it and the situations that we know we can handle with the system. So it's more of an incremental learning approach. And of course, you can use the same metrics like disengagements per X 100,000 kilometers, etc. But it always depends on where are you using the system, right? And today we have AI systems that are geofenced in very limited areas. And with this approach, we want to take it further and increase the operational design domain continuously by adding new skills over time.
Yeah, thank you very much. Great presentation, and I also understand the beauty of the whole system and the setup in general. I think you were just talking about that the number of skills you were looking at would be in the 100,000s, kind of this one. I'm just thinking about like how do you manage then to have like the integration or like the collaboration of like you will pick the one skill or the other or maybe a combination of skills and so on. So like I guess there's also a lot of interface work and which needs to be solved, and I'm questioning like how is this interface work, integration work kind of in real time being operated, and do you also can elaborate a bit about the computing power you might need, which I would assume is going to be higher than a monolithic setup? So it's going to be
yeah, sure. So the goal is, of course, to use less compute than a monolithic setup, because what you see there is similar as with LLMs, right? The training models are getting bigger and bigger, so you have more and more billion parameters in the next iterations of the model. And here the idea is to say, I don't need to have such a huge deep learning it's not a very deep model, but it's actually quite narrow and model trained end-to-end for a specific task and scenario. And then I only use these skills that are needed in this moment in time. So what we did there, also in the implementation, it uses much less compute actually than if you would run a complete deep learning model on it. And then the question is, I think, of course, but the question is, what is a skill? So how do you cut or define the skill in such a narrow way that it's perfect for the situation, but that it's as broad as possible then to cover the situation or as many situations as possible. And that's a bit then the trade-off for the sparsity of the model.
Yeah, thank you, Manuel, for this really intelligent, novel approach. Really like it because that's much easier to validate than the other one. But 2 questions. If you could go back to slide 12.
With the help of...
If that is possible. So there was a nice picture, and actually I really understood it. So you do not have a core. It does not only, you do not only take the agents for the edge cases, you have only agents. There is no core, which covers, I don't know, 99% of the normal driving situation. So the entire system runs with agents, if I understood that right.
Mm-hmm. It runs with agents. Yeah, it runs with agents. Okay. Yes, sure.
And then the second question, what happens if 2 or 3 agents are totally convinced that they have to overtake at the moment? What will you do then? Yeah,
you need to have a redundancy, of course, then in the system to revalidate it. Yeah, so this comes by the design of the system. That's also something that comes then with the confidence intervals between it. So you can try to simulate this, and then it's in the validation process in there. But you still have then explainability in your approach. Why did it do this? And then you can still optimize it. So by design, we believe this is a much easier way than to do this basically in a monolithic way. Yeah.
Oh, yeah.
So you really exchange models during runtime in driving?
Yeah.
Cool.
No, we did have a base model, yeah, so that what Matthias asked, that takes over basic driving tasks. And then we had in the collaboration that we did with some of the automotive players, we looked at specific scenarios. Yeah. And so we overfitted certain skills to these scenarios. And now we want to take it to this next step, yeah, and add more and more scenarios to this. So of course, also this system will be exposed to more and more edge cases, and will see edge cases that it never saw before. But for that, we train specific skills and agents. And for the new situations, we'll have some confidence interval that a certain skill will fit this in the best possible way. And this is how we want to reach this problem.
Okay. Please be aware, it keeps us from the beer.
Okay, very short. The first application in China you're talking about, can you say something?
Yes, so that was on the other AI spectrum that I showed in the beginning. So that is, we're providing perception software into a smart camera. So only with a single camera we provide ACC functionality, autonomous emergency braking, lane keeping assist, traffic sign recognition on very, very low compute. So also there, we already see with our AI approach how that we're using very low compute, we're very efficient in how we do things, and it's a very, very low-cost camera solution because we see a huge market of cars that now will, for the first time ever, get a camera, just like you are used to getting standards in seat belts, in airbags, and we believe cameras will be the second generation of ADAS systems that will become standard, but you need to do it, as we heard in the economic situation, in a very, very cost-efficient approach, and this is also where this technology really excels. Thank you.
Thank you very much, Manuel. I was amazed of all the competency in this room here.